Okay, so today I will teach something more about OLS. So basically OLS is about line fitting. And here what is important is the T statistics for beta hat. Okay? If this value is larger than 2 or less than -2, we think that estimation is reliable. Also, what is also important is F statistics. Okay? F statistics, this one is talking about if your regression result is entirely reliable or not. That kind of thing. And what I taught in my last class is something about multiple regression. So what I asked you is to find your own data set, okay, and run some kind of regression like this. yi equals alpha plus beta 1 x1i plus beta 2 x2i plus epsilon I, something like this. In this case of the multiple regression, sometimes you may get t-stat for beta hat less than 2, something like this. So what matters here is the t-statistics for beta 1 hat, and what if its value is less than 2? There are so many ways. The best way, of course, just believe it, do another research, okay? But there are some other assumptions. So this is purely practical purpose. And it is not recommended to do this kind of things, but in real kind of research, you think, wow, I expected this t-stat for beta 1 is larger than 2. Okay? Then people think this estimation is reliable. Okay? But under some circumstance and in many cases, because of data problem or something else, you may get this kind of result. Okay? Then the next step we have done up to now is this kind of OLS. And OLS has some assumptions. Okay? And one assumption is epsilon I is identically and independently distributed. Okay? This part is identical distribution. So this one is about, oh, not this way. A data set is in some sense distributed like this. Okay? So this means that along this one, they are almost identically distributed. But in many cases, this kind of assumption is not true. You will see this kind of data set so many times. Something like this. Okay? Something has large variance, something has small variance, something like this. If data set is really beautifully distributed like this, ding, 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 ding. Okay? In this case, it will meet the assumption of OLS. Okay? However, in many cases, you do not see this kind of data set. Okay? In that case, by relaxing this assumption, you may get better result. In this case, we are relaxing identical distribution of some assumption and moves on not OLS but GLS. generalized least squares. Okay? So in this case, the core idea is give less weight when the variance is high. This one. When the variance is high, okay, let's give less weight. This one is very widely dispersed, okay, then forget about that or give less weight. In theta, what you do is REG and then Y and X, and there is one option, comma, robust. This option. Or I think also R works. I don't remember. I think R worked. But basically robust. I think only R. Can I see? ROBURST or ROBURST? I think this is the spelling for robust. I forgot it. But comma R, I think generally works. So do you have your data set in your laptop? Okay, then run the regression and use this comma R option right now. Done? And then compare OLS and GLS regression result. Okay? In general, T statistics for the GLS is larger. That value in general becomes bigger because it uses more information. So, you have not done? No. Yeah. Can you do something else? Basically, regression without R at the same time. So T statistics weighted this way. Oh, this is interesting. This one is more likely when you do this kind of different some kind of different. I think price is dependent variable. Okay, and weight and length kind of thing. In this case, this one must be pretty good data set. The weight and length impact those kind of things. But when you control this kind of robust error, okay, so this one is kind of R and this one is generally robust R squared. Yeah, R squared, probability number of observations, yeah, robust standard error, robust, there's no R, yeah. This one is more likely controlling other things and it still shows that weight is more important. What you can see is this kind of coefficient is the same. Okay? Coefficient is the same, but standard error, in this case, this one is getting bigger. Okay? So, in general, we believe this kind of result. Okay? So, the usual case, in this case, is after this one, HET, EST. Yeah.
That is 4.
Yeah.
This is 4.
This is 4. Let me explain one more time. I did not teach that. But anyway, this one is task for heteroskedasticity.
Oh,
This
right.
one.
Yeah.
So this one is checking OLS assumption is correct or not. And H0, the null hypothesis is OLS is correct, constant variance. And this one, reject.
Okay.
So basically the assumption of OLS is not reliable.
Yeah.
Okay? So basically the procedure is,
We run REG at first,
yeah,
then we
regression first, and
Regression,
then
comma,
do
R.
this kind of heteroscedasticity test.
Okay.
And then when you reject the null hypothesis, then you need to run this regression.
Okay.
Okay?
Okay. This comma.
Yeah, so basically OLS is based on the constant variance, but that hypothesis is rejected.
Okay.
Okay? Then we think this one. But people generally use this kind of test in general. But anyway, that's the procedure. Okay? So try to compare the regression result. The first thing is coefficient is the same. Okay?
Yeah.
But standard error is different. In general, what we want is decreasing the standard error. But in this case, when you run something better, this kind of thing is more how can I say? This result is more reliable. Okay? So basically, this one says that weight is more important than length kind of thing. Okay? So in this case, weight is still significant, but length is only 8 to 7% significant. Okay? Sometimes 10% significance is acceptable, but sometimes not. Anyway, this one says that weight is more important. Okay? So that kind of result.
Okay.
Okay?
Got it.
Okay. Let's see your regression result.
Yeah, I tried some other data set, but I
Yeah.
just came back to the data set
Yeah.
they gave
And
us last
what
week.
what is your trial?
Hmm?
So what kind of data set have you used?
The one you gave us last week.
Yeah. Then did you try to find any different data set?
Yes, but
The Syracuse data kind of thing, I guess.
yeah.
Yeah.
Mm.
Then it's not working.
I don't quite understand the logic of the other data set.
Okay. In
Yeah.
this case, then let me do this kind of thing. Oh, yeah.
Or maybe it's not working.
You need some kind of what is it? Like
Uh,
white paper
yeah.
or something else.
yeah.
Yeah. So in this case, basically what we have here.
Oh, this time it doesn't play well.
uh, So basically, this one is the thing, and this is OLS regression region. Okay.
Yeah.
So this one is with robust error,
Mhm.
and this one is without the error. Okay. When you see this kind of pattern is more likely to be general, the coefficient is the same. Okay.
Yeah.
But when you control this kind of the robust kind of option, standard error is getting this one is smaller.
Yeah.
Okay. Previously it was 2.76. Now this one is 2.2.
Mhm.
And because of the relatively small standard error, this t statistics increase.
Increase.
Okay.
Mhm.
So this is something what happens in general when you control this kind of heteroscedasticity generally.
Mhm.
Okay, and then the HT EST. So this is some kind of test for heteroscedasticity, and this one basically, oh, interesting. This one basically accept the null hypothesis.
Oh.
So in this case, OLS is the test says OLS is fine. Okay, and that's not a big problem. Okay, this one means that something relatively okay, but usually what happens is that you reject this kind of test and then run this kind of robust error,
Mhm.
then you may get some different result.
Okay.
Okay,
Mm.
so what I want to show you is this kind of coefficient is the same,
Mhm.
standard error is changing.
Mhm.
To check if I can use this robust error or not depends on this kind of heteroscedasticity testing result. In this case, interestingly, you accept the null hypothesis. Then in general, OS is fine, but still people want to see this kind of result. Okay, ready? So this is your regression result. This is the robustness result. Okay, and when you see this kind of thing here, the coefficient is the same. Okay, what changes is this kind of robust error. Okay, then it changes t-value as well. Previously this one was pretty big, now it's relatively small. Okay, because this value changes, this t-value also changes. Okay, so that's the option for robust error. And in general, what we do is this kind of when we run this kind of OS regression result, next step is HET-TEST. This way. So basically this one is the heteroscedasticity test.
So the order is the same, the
Yeah.
T,
That is t-test.
T-test.
Yeah.
It's the same?
The t-test is for this kind of one coefficient. Okay? So it is doing this kind of test for this one. HET test is for the heteroscedasticity. So this one basically what means is the constant variance kind of thing. Okay? Constant variance is data set is something like very constantly distributed. And it says no, that's not the case. You reject the null hypothesis. This value is unbelievably big. Meaning that H0 is rejected. Okay? After rejection, you can use this kind of robust option. Okay? Then this one is more reliable. Okay? Yeah. So what I explained as the general case is that basically you run this kind of OS regression first. Okay? This is your first step. And then we use HET-TEST. This is heteroscedasticity test. Okay? So this one means that the other way is homoscedasticity test. This one. Okay? Where's my coffee? Anyway, oh, there. Okay. So this task, this command, it only works after you run ORS regression. Okay? Then, when you run this kind of ORS regression, you get the estimated value of epsilon I. Okay? When you run ORS, now you can estimate this kind of errors. Okay? And then it checks. Can we trust this kind of identical distribution? In HE test, it says H0 is constant variance. Okay? Constant variance means that variance is identically distributed. Okay? In other words, ORS basically assumes when you run this kind of data set, it's distributed in this way. Okay? Very constant variance. Okay? For this value, data dispersion is the same. Okay? In this case, that is the null hypothesis for the constant variance. ORS assumes data set is distributed in this way. Okay? And based on this assumption, we run ORS regression and we estimate the value of error term. Okay? Then now we know this value. Then based on this value, we can run HE test, heteroscedasticity test. This kind of hetero means that data set may be distributed not in this way, but something like this. Like this, okay? Small variance, large variance, small variance, small variance, very small variance, very large variance, small variance, like this. Okay? Then this is kind of visualization, basically assuming that this one has small variance, then this one is more reliable. Then let's give more weight to this point. These guys, they have large variance, meaning that, oh, this data set may have some problem. Then why don't I give less variance? Okay? So HE test is checking if the data set is distributed in this way or this way by checking this kind of estimated value of residual. Okay? So when this one is true, then OLS is totally fine. OLS assumption is data set is evenly or this kind of homoscedastically distributed. Basically, this kind of homo means very similar. Okay? This kind of hetero means that data set is distributed in this way. Okay? Then, by running this kind of heteroscedasticity test, we can check this one OLS or GLS is correct. Okay? So if you reject this one, basically in this case, what kind of value do you have? I think it's generally the p-value. Yeah, chi-square. So this one, this kind of test, basically you estimate this value of this one, residual. Okay? Then there are some positive terms and there are some negative terms. One also square it. Okay? When the distribution is very homoscedastic, okay? One is independently and identically distributed. So these values, they should be very small. When you follow this kind of null hypothesis, chi-square value should be small. Okay? But when data set is distributed like this, okay? Sum them up, that value is also very big. Okay? So when you have very big, then you reject the null hypothesis. Okay? That means that data is distributed very widely, like second diagram. Okay? That's what I mean. There are some big, large residual. You square case, where is your, yeah, this one. In your case, chi-square value is unbelievably small. Okay? Meaning that all the residuals are very, very small. When you square it, it's still small. You sum them up, it's still small. That means that first kind of distribution is more likely to be correct. So you can still use OLS. Bigger. Okay? And when you sum them up, that value is still very big. Okay? So you reject this kind of constant variance